Okay, we're going to talk about using analog read on the Arduino, and the way it works on the Arduino, there are 6 different pins. They're A0 through A5 that you can use for reading analog signals. Now, a digital signal is an on-off, a high-low, a 0, 5 volts. Okay, an analog signal is something that varies. Say a voltage that can vary, be 0, 0.1, 0.2, all the way up to 5 or 20 volts, or whatever you happen to have. Okay. Now, I don't remember the exact range that the analog pin can read. I think it's 0 to 5 volts on the Arduino. But what's really important to know is that the Arduino has digital or analog to digital converters. And so what it does is it basically samples it. A minute ago I said 0 to 5 volts, 0.1, 0.2, 0.3. Well, could it really have that level of resolution? Well, it depends on how many bits are used. Because when you read an analog signal, you got to give it a number in the Arduino, not an on-off status, right? So if you're going to give it a number, you have to know how many bits you have to work with to represent the number, right? I mean, if it's 2-bit input, then we can only have, what, 4 different levels of voltage off, right? 0, 0, 0, 1, 1, 0, and 1, 1, right? So that's not very good resolution. That would be less than a volt of resolution on a 5-volt scale. Because you need it to represent 0 volts with 0, 0 and 5 volts with 1, 1, right? So the other voltages would be, you know, a quarter of the way along that scale. So anyway, the digital to analog converters that read the analog signal in the Arduino are actually 10-bit DA converters, or AD converters, and analog to digital. So if it's 10-bit, how many different numbers can we represent with 10 bits? 2 to the 10th power, right? So 2 to the 10th power is what? You can grab a calculator if you want. If I remember right, it's 1024. Okay, because you can. I have it memorized that 8-bit is 256. Okay, so if we multiply that by 2 for 9 bits, then we're at 512. 2 more, or multiply by 2 again, we're at 1024. Okay, so 10-bit is 1024 different levels. So grab your calculators, please, or your phone, or whatever you use for your calculator. So if we can represent 1,024 different levels, where one of those levels is 0, so 0 to 1023, what would be the resolution of the voltage if we're talking about a 5-volt scale? Well, here's how you figure it out. Take 5 volts and divide it by 1024 or 1023. It doesn't matter really. What do you get?
4 thousandths or 5 thousandths of a volt.
5 thousandths of a volt. That's a decent resolution, right? So could we detect the difference between 0 and 0.1 volts in the Arduino? Absolutely, because our resolution is 4 thousandths of a volt, right? So we could detect a voltage change as small as 4 thousandths. So we could detect 0 volts, 4 thousandths, 8 thousandths, 12 thousandths, so on, right? Now, of course, it's rounded off the way I'm doing it, but hopefully you get the idea. So that's pretty good resolution. And you can see why they didn't waste 16 bits on the input, right? Well, why would you need 16 bits of resolution? That'd be very fine voltage. In fact, what you'd have to do is take the 5-volt scale and divide it by 65535. You got a calculator, go ahead and do it. What would the resolution be? So if they used a whole 16-bit word.
700 thousandths.
So in the 100,000ths place of a volt. There's definitely more noise on the line just from the electronics being around the wire and inducing current into the wire that would vary the voltage by that much. So there's no point in having 16-bit resolution. Okay, you'd have to have shielded wire if you wanted to have that finer resolution and actually mean anything and not just be picking up noise. So there's no point. This is just an Arduino. It's just a small microcontroller. Why bother? What about if it was 256? So 8-bit. What if they said, well, we don't want to waste 10 whole bits. Let's use 256 instead. So let's take 5 volts and divide it by 256, which would be 8-bit resolution.
So basically 0.02.
0.02 volts. And they probably thought, well, that's probably not good enough resolution for some applications, so let's make it 10-bit resolution, which is very common. A lot of sensors, a lot of things are 10-bit resolution because that seems to be a good resolution. Anyway. So we want to somehow get analog input into the Arduino, and for this last lab, after this we'll call them projects, but for this last lab, we've got to get an analog signal into the Arduino in order to control the speed of the stepper motor. So we'll do that very simply with a potentiometer. Okay, all we're going to do is use a potentiometer to generate a voltage between 0 and 5 volts. How do we do that? Well, first of all, you need to know a little bit of something about the way that a potentiometer is set up. The common potentiometer is set up like this. A linear potentiometer looks a little different, but we're more interested in this type. Basically, it's a variable resistor. There are 3 terminals. There's a center tap where you have a wiper that can touch the resistor along any position. So if the wiper is here, there's low resistance between these 2 points. As the wiper moves around, the resistance length gets larger, and so the resistance gets larger, but the resistance on the other side between these 2 terminals falls. Okay? So one way you can set this up to generate an analog voltage is to simply set it up as a voltage divider. So you could put on one leg of the potentiometer, one extreme end, say the extreme left, you could connect positive from a battery, and the other extreme end connect negative, and then just measure the voltage from ground up to the wiper. Okay? And as you move the wiper up closer to one terminal, well, then the voltage there against ground will actually increase. And if you move that wiper down closer to ground, then the voltage will move closer to ground. Okay? So it's a real simple idea, and it is useful. Now, fortunately, there's already a really nice, simple, I didn't even have to code anything. There's already sample code in the Arduino, and I wanted to show it to you. It recommends a Arduino with a 10K potentiometer. Well, I've got a potentiometer that I pulled out from the junk I've got in the back. But the question is this really a 10K potentiometer? Would it have to be? Well, it wouldn't have to be, but I'll explain why they chose 10K in just a minute. If you look on the side of this, it says R103. Any guesses what that might mean? R is for resistance.
103 ohm.
You'd think, but remember the way that resistors are coded with the color coding? Usually your first 2 colors are a number, but then the next one is the number of zeros. That's the way this works. So 1 0, and then the 3 means 3 more zeros. So this is in fact a 10K potentiometer, which is very common. Now why choose 10K? Why not choose 1K? Why not choose 1 ohm? Because if you set it up with the schematic I showed you a minute ago, it would still serve as a voltage divider. It would work just fine. Well, if you have a lower resistance, there's going to be a lot more current flow. Does that make sense? And the Arduino pins can only provide so much current. So with a 10K resistor across 5 volts, how much current would this thing be pulling? Well, it equals IR, all right? So we take the voltage, 5 volts, divide it by the resistance of 10,000 ohms.
Is it half a milliamp?
It would be half a milliamp, that's right. So this is only pulling half a milliamp. Okay, now the pins, I misspoke a minute ago. I was thinking of the input pins as providing current, but they'd be sinking current, because this would be providing a voltage to that input, which would then, through the Arduino, go to ground. Okay, so at most, it's going to be a half of a milliamp, right? So really, the reason for the 10K is so that we don't drain the capacity that the voltage regulator has on the board. It won't have to provide very much current for this to make it work. Okay. Anyway, so I just connected it in accordance with this Fritzig schematic. You can use the same wire color, so hopefully it would make the most sense. And if you go into the Arduino IDE, in the examples, under analog, there's analog input. And so that's the program that I opened up. Okay, here it is. And it's a real simple program. All it does is it says, let's use, no, it's off the screen, hang on. Try again. It's using pin A0 as the analog input, using pin 13, the built-in LED, as an output, and declares sensor value. So here we're setting the pin mode for the LED, so it is an output. And then what it does in the loop, let's scroll down so we can see the whole loop. What it does is it uses the analog read command. This is the command you'd use to read the analog sensor pin. This is where we're going to have our voltage connected. And in fact, I can pass this around if you want. I'll hold it up for the camera as well. What you'll notice is that the black and the red wires are connected to ground and positive voltage. So the black goes to ground, the red wire goes to positive 5 volts. Now you'll notice also, if you can see it on the camera, that black and red wire are on either side of the potentiometer, and the wiper is the blue wire, which goes into analog 0. So I'll pass this around and let you guys look at it. It's exactly like the schematic showed. But basically what's happening here is sensor value is set to reading the sensor pin. So before, if you were doing a digital read, you would get back a 1 or a 0. But since we're doing an analog read from an analog pin, we get back a value. And now, what would be the range of this value, sensor value? I told you it's a 10-bit port. So what could the range of sensor value be? Any ideas?
0 to 1024.
Exactly. Well, 1023. 0 to 1023 because you got 1024 numbers. Right. So we're going to get a number back that is from 0 to 1023. Okay? And then what they do is they turn on the LED and just delay for however much they read. So the higher the voltage that is read, the higher the sensor value will be, and it could delay up to 1023 milliseconds. So that's a little over a second. All right. Thank you. And then it turns the LED off, waits for the same amount of time, and goes back and does the whole thing again. So it's constantly adjusting the cycle time of the LED based on the voltage that it reads. Okay, it's a very simple program. Let me plug it in. You can see it operate. I've already downloaded it. And so let's see if we can show it on the camera. Yeah, there we go. Now, the connection, if the connection's broken or the resistance changes, that changes the voltage on that pin. So this behavior can be a little bit erratic. But right now, the potentiometer is turned all the way clockwise in your view, and you see the LED flashing on and off fairly slowly. As I turn farther and farther counterclockwise, what I'm doing is I'm decreasing the resistance on one side. I'm basically putting in a lower number, decreasing the voltage, okay? And you see the pin flashing faster. Okay, or I'm sorry, you see the LED flashing faster. In fact, if you turn it all the way to the extreme end, you basically see the LED, well, it looks like it's just on solid. That's because it's turning on and off so faster and my eyes can't see it pulsing. Okay, and as we turn up the turn up the potentiometer, in other words, to get a higher and higher voltage on the pin, what happens is the LED flashes slower. Okay, so that's how you can get an analog signal into the Arduino. Remember, our goal is to use the sensor value essentially to control the speed of the stepper motor. So this will be a variable that we can use to control the delay between steps, and that's how we can control the speed. Does that make sense? Any questions? It's pretty straightforward. Just remember you're looking for analog input, and you can look on the Arduino's website and see the circuit and see everything else. But you see here essentially we've got 5 volts on one side of the potentiometer, ground on the other, and then the wiper connects to the analog input on pin 0. And that's about it. It is one thing to note that is important. It is important that sensor value not be a Boolean type, because a Bool type can only have values of 0 or 1. It needs to be an int or a float or something that can hold a number, preferably an int, because you're going to get an integer back. It's going to be an integer from 0 to 1023, and so the safe space to make it an int. It could be an unsigned int, because you're not going to get negative numbers, but that doesn't matter too much. All right, well, that's it. I'll stop talking.